Scheduler.yield is almost here. Just sprinkle the simple line into your JS code frequently to give the browser breathing space and avoid initial next paint issues. Await scheduler.yield. Importantly, it allows continuation of your code to be prioritized so you don't lose out by yielding. What is yielding? What is going on here? And why should you care? Well, honestly speaking, I don't think many of us as end developers building applications will have to think about yield too much, but that's because it wasn't built for us. This API was built for one specific team, the React team. And after years of collaboration between Chrome, web standards committees, and the React team, it's finally super close to shipping. And I think it's worth understanding what it is, why it exists, and what can be done with it. On the topic of yielding, I'm going to have to ask you guys to yield for a second for a quick word from our sponsor.
Door troubles? I've been there. You should check out Unkey. That gonna help with... Unkey's the best way to build APIs fast. So if you need to make sure that your customers are hitting an endpoint and doing it securely, there's no better way. They generate the keys for you, they manage all the security, they even have a rate limiter built right in. They handle millions of requests for just dollars. And if you want to build a great API for your users, especially if you're building some new AI app, you shouldn't be wasting your time on all that verification stuff. Oh, and if you're worried about giving all of that type of stuff to some other person externally, don't worry, it's all open source. If you want to host it yourself, you can do that too. But honestly, I'm probably just going to use the product online. It's so cheap, why not? Protect your API today with Unkey.
Sunil, famous from being on the original React team, React just can't stop winning. The API and implementation is the result of a multi-year collab effort between Meta, specifically the React team and Meta, as well as Google Chrome and many others. And it underpins React's concurrent mode, now being implemented in the browsers as a standard. Huge. Huge. So before we can dive into how this works, we need to think about the event loop a bit. At this point, I would say the event loop video. What the heck is the event loop anyway? This is an essential watch if you're watching this channel. And if you haven't watched it in the last year, probably worth watching again because it is phenomenal. And understanding how the event loop and call stack in JavaScript work will make understanding all of these things much easier. I also didn't realize Lydia Hall did a video on this 5 months ago that is more popular than any video on my channel. Good for her. Huge. I haven't watched that one yet. I'm saving that for later for sure. Apparently, people are saying that Lydia's video is even better than the JSConf one. That's nuts. Watch both. This is legendary, and Lydia's really, really good too. I would say watch both. I have to presume that you kind of know the event loop, or this will be basically impossible to do, but we'll go with it. So let's pretend we have a basic React app. We have the call stack and the task queue. Task queue is things that need to be done. Call stack is the thing currently being done. And the event loop's role is to take things from task queue and put it on the call stack. Let's say we're doing a complex render. We will render this as red, put it in here, and say complex render. This complex render is like React re-rendering your whole app or a state change that triggered a bunch of things changing. So this is going to take a second to happen. Let's say while that is happening, the user did a small thing like pressed a key in an input field. So I'll make this actually smaller because this task should theoretically be much smaller. And this complex render is meant to be big. So if this is happening in the call stack right now, and this thing takes a lot of time, this input cannot happen until this is done. There is no ability for this input to interrupt what is going on here, which means if you have like the classic demo of like an input field where you're typing, and every time you type a letter, it causes like, I don't know, a search to go off and to update the page with a different set of things on it. The classic demo is with the color picker thing that they did in the React Conf compiler demo. This is a to-do example, like a to-do list, and as the input type is color. And with this input type is color, it's going to change a lot when you're changing things because you're dragging the cursor around and every frame it's sending a new state. And if we look at the state here, the theme color is being passed and we're keeping track of it in this to-do list like wrapper. So when the state changes, it has to re-render the whole to-do list, which means it's blocking that whole time.
And we need a second prop named the theme color so users can pick a color to theme the user interface. If we try this code out, it works, but the app feels pretty laggy.
Do you see the lag happening there? Where his cursor's here, but it's still many positions before? That's because the state being up here forces the whole to-do list to re-render before it can process the user's input. So we're effectively creating a bunch of inputs on the task queue for all these changes that can't happen until this complex render is done. This happens, it takes one of these, it does it, and then it immediately has to pull this back up again before it can process any of the additional inputs. That sucks. Shit, we got Ryan Carniato in chat helping out. Legendary. As he mentioned here, it causes every component to re-render, and he dropped this original example here with the OG React Fiber, where they were handling things with concurrent mode. Nuts. Do they have a non-concurrent example? If I go to here, yeah, the stack example. So notice how much slower this one is because the browser updates and the React updates are blocking each other. With a Fiber example, it lets you run things in parallel effectively, but the interruptions are much more important, which is what we're here to talk about. It was based on hover on the triangles and the count updating. So yeah, the hover is the interruption. Okay. Oh, the hover is the action that's interesting here. It's doing all of the triggering, all the updating. React is just doing its thing, but hovering is an interruption that would have been blocked if this wasn't able to run concurrently. That makes more sense. Okay. So in the non-Fiber example, if I grab this link again, the big difference that we care about isn't just how much slower this moves, it's how much longer it takes to hover and like do the hover behavior, because it can't do that until the render happens. So the render is blocking the user actions, and the user actions block render. It's like a back and forth of everything blocking each other. God, my whole computer was slowing down from that one. And here it's much smoother because it can allow for user actions to interrupt. But the React team wanted to go way further. They wanted the ability to just programmatically call interruptions whenever they felt like. So to simplify what is happening here, to simplify this change, imagine that this complex render could bail out at certain points. If at a certain point during this complex render, we could just draw a line in it and say, hey, at this point, pause, pull things off the queue, and we'll get back to it in a second. You're effectively saying, hey, take the rest of my task. So if I break this up into multiple parts now, if we call yield, what we're doing is we're taking these other parts and we're putting them back in the task queue. So if right now we only have like these two inputs the user did, and we have this render going on, and we call the new code scheduler.yield. What we are saying to the JavaScript runtime is everything above here, just throw it back in the task queue. So now if there are other things that need to be run, like we finished that, and now we want to deal with the input field, cool, we throw this away, we do this, we finish it, we do the next input, we finish it because those are easy to parse, and then we throw this back on. And as long as this code is smart enough to say, oh, things have changed since, let's make sure we're rendering things post that change. Now this can all be cleared through, rendered correctly. Maybe one of these tasks even says, oh shit, everything's changed. We have to go back to the start. So when complex render 2 triggers, it says we have to redo everything, and it just brings all 3 back into the task queue where it can start pulling them from there again. But the important piece here is that it didn't put 3 things in the task queue initially. This was all one box. It was all one task. But when you call schedule.yield, it turns one task into multiple by taking whatever happened after the schedule yield and throwing that back on the task queue. You're temporarily moving the execution out of the way of the thread. This is a huge change. This allows for people to make their own React, so to speak, significantly easier because you don't have to build your own crazy threading model. You can just yield regularly in the code that might be blocking, and it will no longer be blocking. If there's nothing left in the task queue, it will just leave these here and continue until it finishes. But if there's anything else in the task queue, it will get interrupted and move back there temporarily. To go to Lydia's video, because it is phenomenal, the way the event loop works is when there's nothing in the call stack, it pulls from the task queue. This is the opposite. When you're in the call stack and you call schedule.yield, it checks, is there anything in the task queue? If there is, move this back there. And if there isn't, just keep executing as you were. It's cool that this is arguably, conceptually, the opposite of the event loop, but I think that is what makes it so strong, and it's certainly what makes it so exciting. I cannot wait to see what people do with this. I did see one blog post of people showing it. Umar from Debug Bear. The scheduler.yield method is used to yield control back to the browser scheduler, allowing other important tasks to run. It's the browser that decides what's considered important. This can be useful when you want to ensure that your JS code doesn't block the main thread and negatively impact the user experience. You might be wondering, what other work does the browser need to do? The scheduler is responsible for a lot of things, like rendering the page, garbage collection, importantly, handling user input. Let's focus on the last one, user inputs. Oh, that's funny. It's an Excalibur of the same concept. This absolutely fits. Thank you, Debug Bear and Umar, for writing this. We're definitely going to take advantage of this. If you want to read the whole post, it'll be linked in the description. So previously, you'd have a long blocking task, and you have to wait for that before the user input gets processed. But now you can chunk that long thing, and user input and other important tasks can effectively interrupt. But it's not a traditional interruption where you're blocking your thing. It is an event loop style interruption where things are being moved from the execution window over to the task queue so something more important can execute in the interim. If you find the terms main thread, browser schedule, and blocking to be confusing, know that you're not alone. Traditionally, web performance was centered around network performance, but as web apps have gotten more complex, the focus has shifted to runtime performance, especially for JS-heavy web apps. The main thread is a browser process that handles different tasks like rendering the page. The scheduler is what decides what task to run and when. And blocking is when there's a task in the main thread that prevents other things from running. All makes sense so far. So here's an example of a blocking function that's slow. You have start time and you pass it a duration. We all know the right way to do this is with a set timeout, but when you do it like this, you are blocking the JavaScript execution until this is done, because this while loop is just going to run nonstop until the condition is passed. So what this will do is block and prevent updates from happening. So if I had like an input field and this was running, I wouldn't be able to type. It would just lock up in the process and it would be miserable. So here's a basic example. This function blocks for one continuous second, 500 milliseconds, and then 500 more milliseconds. But if you put a scheduler.yield in the middle, now you'll see in the performance view here, without yielding, it's just one second task. But with yield, it can be broken up. So if the user does something in that time, that can happen in the in-between. So it's not on in the browser by default, by the way. This is part of the 129 version of Chrome beta. Do I still have Chrome beta installed? I do. Let's get that updated so we can give it a shot. I'm clicking one long task, and now I'm clicking accept cookies, and nothing is happening. And there's all my cookies after the task is done. If I refresh, oh, it's still blocking. That's hilarious. Cool. Now I'm going to do many smaller tasks, and I'm going to click. It's still slow, but they're happening in bursts now because the smaller tasks are yielding to give room for my inputs to be processed. Before, those inputs wouldn't be processed due to the nature of how the scheduler works. If we break this down in the performance view, this is where things will get fun. Well, let's record a performance profile. If you haven't done this before, you should. It's fun. I'm going to hit the one long task, hit a bunch of accepted cookies. Nothing is happening. And here we are. Let's stop the profiling and see what this looked like. See this giant task, and then here, all of the event clicks process, and then all of the commits happen after these tasks. Very painful. And if I switch to do many smaller tasks this time, we're going to record a new profile. Many smaller tasks, accept, clicking it a whole bunch. Stop now that we'll see that. And here we can see a very different call. These tasks are much smaller. And if we zoom in on any one of them, we can probably see the commits happening in here. Yeah, the event click, it's right in between the two, but you can actually see it. And the fact that that can happen and be processed despite these tasks, that's a huge change. Ryan Carniatos, once again, calling out really important things in chat. The important thing is that this is different from scheduling a microtask because microtask queues don't yield to macro tasks. It will run all the microtasks before the next macro task. It isn't unlike occasionally using a set timeout 0, but the behavior can be different if there's nothing important pending. And that's the key, is importance. When you call scheduler.yield, it's not just doing the crude demo I showed here where it's throwing it back on the task queue. It's taking advantage of the prioritization the browser is capable of. It knows which tasks are important enough that they should execute sooner, and you're letting it do its thing. You're saying, hey, I know my task might seem important, but I'm telling you, it can stop right now, do any other important work that's waiting, and then we will continue in a minute. The before demo blocks the main thread for 1 second 3 times. And the after demo will await the scheduler.yield calls in between. And the actual interactive button, the one that makes the cookie, also triggers a block. I almost want to delete that because I think it'll make it slightly clearer. I kind of want to take the time to make a better version of this demo. There we go. My version of the demo. Nice. Many smaller tasks. Accept. Now they're coming up almost immediately. There's still the up to half a second delay, or the second or whatever it's configured to. But if we stop and look at this now, you'll see what I would consider to be a much more interesting breakdown, because after demo is blocking constantly, but we can sneak in these tiny little events in between. If I zoom in to one of those, see main thread blocking, but if we get in between here and get really close, these tiny little updates, the paints from the clicks, can all happen between the microtask. And that's the key, is now we could sneak those in between, where previously, if I re-record this with one long task and click a whole bunch, nothing is able to happen. And if we stop and look now, you'll see this long task went, and then at the end, all the updates could happen afterwards. As always, Ryan is making very important points. If you replace scheduler.yield with putting the rest of the routine inside of a settimeout 0, you would technically get the same impact for something like this. But the scheduler.yield API is nicer because uninterrupted, it can continue on the microtask. And that's, again, the key difference here is theoretically, if I go back to Stack Blitz, for this example, because it is so simple, I can change this to be set timeout 0, comma, block main thread, set timeout 0, comma, block main thread again, delete these, and move this to be at the end here. Oh, I did the order wrong. That was very stupid of me. Sorry, I'm bad at JavaScript. There we go. If only we had a type system that could tell us when we made mistakes like that. Fix this code. Now we have the function, but we have it under a timeout of 0, so it should immediately execute, but the separation here is triggering it later. So if we rerun this one last time, many small tasks, accepting cookies, and they come in chunks because it has the free window. And now we see basically the exact same thing. You'll see all the updates happened in between. Many small tasks, then one long task. Now I'm accepting cookies. And this long task had to block everything there. So see that long one right in the middle? Because that's now allowed to block when it's not the microtask queue. But if I had reverted this back, which I will, it'll take a second. Now, this will probably be the most interesting demo. This might be the one where it clicks. Small tasks, accept some cookies. Long task, accept more cookies. And these cookies can all come in before that long task starts, because yield is saying, do the important tasks, not the long blocking ones. And it can sneak in all of your click events before it triggers that long task, because this task is lower priority than the inputs. That is really cool. And thank you, as always, Ryan, for giving me the opportunity to show the actual difference here on a much deeper technical level. It is the macro versus microtask part. Back to this article, it's actually super helpful. As we see here, the tasks can be handled significantly quicker. Canceling a scheduled task after yielding with a task controller. Ooh boy, I didn't even know about this. This is super cool. I assumed it was there, but I hadn't seen it. The continuation of work is that the code runs after the scheduler yield call. You can cancel this continuation by using the following: the abort method of a task controller, the post task method of a scheduler object, and the signal option of a scheduler.yield. Look at that. Signals. Always good to have Ryan leaking into everything, right? The main point to highlight in the following code example is the user can start a long-running task by clicking the start button, but the user can also cancel the task by clicking cancel. So we have block main thread, scheduler.yield, signal, inherit. The task using the scheduler passing the signal from the controller. The inherit option means the task will inherit the signal from its parent. So if we create a scheduler above, in this case scheduler.postTask, that will now be a signal that can be tracked. If we want to cancel it later on, we can call the same controller, but this time .abort, in order to cancel that. The let controller. So we've made this controller a global, effectively. We bind it when we create the signal from the user clicking the start button, but then the cancel button can cancel at any point. It doesn't literally cancel you in the middle of the work. It only cancels during the await scheduler.yield section. But again, if we're thinking about React, imagine it's doing a big, heavy render to update your whole page, but then it yields for a second and sees, oh, you changed the state. All the things I was rendering don't matter anymore. I'm going to re-trigger this render, stop all the work I was doing, and do the right render this time. That is magical. It makes writing your own React or things like it that perform as well trivial. This is so cool. Oh, he even has a demo of the cancellation. And again, you need to be on the Chrome beta for it. Cancel, clear, record, start work. And it tries to run 5 chunks of work. And when you cancel, it won't run all of them. Chunk 1 ended, chunk 2 ended. I can cancel after chunk 3, and now it will cancel before it gets to 5. Super, super cool. And again, we can see here with the blocking work, we do the first one, we do the second one, and then my interruption, which was on the queue waiting, gets processed, and it has a cancel, which prevents the rest of the work from being done. Super, super simple. This is really cool. It is important to note, though, as you've seen from me hopping between browsers, it's currently an experimental web standard, so you need to opt in before using it. You can do that locally or signing up. It is now default in the newest Chrome beta, so it's no longer just behind a flag. We're making a lot of progress. I actually have pulled up here the Chrome 129 beta notes. It is part of the official latest Chrome beta. It's happening. It's time. We're getting there. But this is not ready to use in production yet. Apparently, you can get special permissions from Chrome to use this flag early by requesting to be part of the origin trial, which lets them put your website's origin in their set of ones that are allowed to access this early. Also, to Ryan's point earlier, if you use the set timeout or just do a quick promise resolve like this here, you're effectively doing the same thing when you call this await there. It no longer has the priority benefits, but at least you can interrupt and let other work take precedent. They call out the exact differences here, where with scheduler.yield, the continuation of work is placed at front of the task queue, but with set timeout, it's placed at the end. So if there's other work that has to be done that isn't priority work, this goes after it. So we have our complex render going on in the call stack. And then in the task queue, we have these 2 inputs that have to be processed, and then another much longer piece. If we call schedule.yield, effectively, we are taking these other parts and we are inserting them here, in between. So we can process the events, put these in, run them. Then we move this here, and then immediately put them back on the call stack once those events are done. If we were to do the other example where we called set timeout instead, these tasks don't go in between the events and the complex render. They go after the complex render. And that's the key difference, is whatever other complex tasks exist in the queue, this would all go before the additional complex task. If you call set timeout, this goes after like any other promise would. If you want a more complex understanding of these things, I will once again reference both Lydia's video as well as the what the heck is the event loop anyways. Both, once again, essential watches for any JavaScript dev. You'll learn so much. And you don't have to do the same thing I'm doing, which is rely on Ryan Coniato to tell you what you do and don't know. That's actually a really good example. So scheduler.yield, we have the timeout callback, yielding with scheduler.yield, continuing after schedule.yield. Since we put this timeout thing, this is now on the queue. So we don't want this to be interrupted with our code. So our code is running, it does this, it yields, and then it does this. This task should not take precedent over the work that we were already doing. So now we get this first, then this, and then this task from the set timeout can run. But if we're using set timeout in these promise calls, this other random thing we called set timeout on, or whatever else going on in our code base, those are now able to run in between. So here we end up with yielding, then the timeout callback, then we get to continue our work. But notice the difference, as they call it in the article, where the continuation happens. The timeout goes in between when you use set timeout or promises to DIY this, but it gets scheduled after when you call scheduler.yield. That is a really cool thing. And since this article was really helpful, I will give DebugBear their opportunity to plug how DebugBear helps monitor the impact of scheduler.yield. DebugBear is a web performance monitoring tool that helps you track the performance of your web apps. They show you interaction index paint scores, specific interactions, visualization of your total blocking time, and your CPU activity as well. When you use scheduler.yield, you can monitor the impact on your web performance metrics. They even have real-time monitoring to make that clearer too. The Debug report shows you the activity that was blocked by the CPU. You can view it on the timeline. That is a much nicer view than what I was just dealing with in Chrome. Good plug. Good shit. Huge thanks to Debug Bear and Dumar for doing this one for me. Makes my life a lot easier. If you want to read the whole article, linked in the description as always. Thank you for Ryan for making me seem like I actually know what I'm talking about. And thank you to Excalibur for making my life easier with these diagrams. As well as a thank you to our sponsor. Makes all this stuff possible. This was really fun. I can't wait for this API to ship for everybody and hopefully to find its way into other browsers too. And until next time, peace nerds.